I'm Sierra from BHIS, and I'm here with Paul Clark. If you just joined, and he is our guest presenter today, so thank you. And if you have questions, go ahead, just type them in the question box. I will either reply, and if I don't reply right away, it's because I'm just going to hold on to it until Paul comes to a good place where I can ask him those, and they'll get recorded. And if you have other good things to share with us, go ahead and also put them in the question box. And also, we'll be giving away a t-shirt. So stay tuned towards the end when we announce that. And without further ado, let me make Paul here the presenter.
Okay.
And then you can just click on the little present button and away we'll go.
Show my screen. So you see a bunch of stuff there, hopefully. Let me go ahead and
do we have anybody on that's never been on a BHIS webcast before? Because I'm always really excited to, I mean, all of you guys that repeat are awesome, but hey, Samson hasn't. Hello.
Hello,
Thank
Samson.
you for coming.
Yes, thank you.
Everybody, thank you so much for showing up today. All right, cool. Go for it, Paul.
All right, so I assume you're seeing the slide.
Yes, we are.
All right. Well, as you just heard in the introduction, my name is Paul Clark from Factoria Labs. I'm here to kind of give you a quick start on the SDR experience. We won't get a chance to dive too deeply, but hopefully, sorry, just having a little keyboard mouse thing. I will spend a little bit of time talking about me, not much. Talk about what SDR is, because I think a lot of folks who registered for the podcast weren't entirely sure or had a vague idea. Also talk about why you should care about it, and then go through the different types of hardware that you might find useful, give you some advice on choosing and installing the software you'll need, and then I won't have time for a demo, but I will sort of give you a really high-level view of some of the cool things you can use gnuradio for in a walkthrough. So, and then we'll have a time for Q&A. So I'm an engineer, and that's proof right there. I have a company that we talked about, Factoria Labs. You can see Twitter handle, GitHub, website there. I think that's the main thing, though. It's a very engineering-focused company, trying to understand the kinds of things that we can build, the kinds of things that we can do with SDR. It's really just a fun technology, and it's kind of why I shifted from the chip designing stuff I used to do to SDR. It was just so many cool things you could do, so much power, and yeah, the kind of that fanaticism about SDR led to authoring some books with my brother. We got 3 volumes on kind of basic stuff, on analog SDR and digital SDR, and then the 4th book coming out later this year. We'll talk about the art and science of reverse engineering. And we also teach some classes, the Hackin' Fest last year, the Black Hat coming up, like we said, public trainings, and then we do some consultancy as well. We had some really cool UAV RF projects last year, working on some LTE stuff right now. So tons and tons of possibilities in this field. So to get to that first question, what is an SDR? The highest kind of simplest kind of elevator pitchy kind of definition is that it's a chunk of hardware that kind of lets you suck radio signals into your computer so you can mess with them on the receive side. And then on the transmit side, it lets you kind of build radio signals and shoot them out of the computer through this magic box. And that's the first level. You can kind of see even in the little image there, just little bits kind of emanating from the computer turning into a radio wave. That's kind of the highest level maybe to think about it at. If we want to go one level deeper, and this is what I call the lapsed engineer's definition, basically you can kind of think of an analog to digital converter that captures these analog radio waveforms, digitizes them, and that lets you process them on a computer using a bunch of digital signal processing. And then it kind of conversely works in reverse to do transmission using a D to A converter. Now this isn't exactly correct, but it's kind of that level deeper of thinking about it or maybe understanding what's going on. And then we have the more formal definition, which I'm not going to read, involves analog front ends and quadrature modulation, all sorts of stuff. And then there's kind of a converse definition on the transmit side. So you don't actually have to really grasp that last one to work with SDR, and that's kind of the main thing. This is not an engineer's electrical engineering only technology. This is a very accessible technology and capacity for all sorts of folks to pick up. And so kind of the big picture, I think, is that you have to have a little bit more understanding that first definition. But you don't have to really grasp all the engineering stuff to be able to use this and to be able to use it effectively. You just really need to know a little bit more about how the analog part of the SDR works. And then after that, you're just dealing with software. So that is the approved definition from my perspective. I also wanted to spread around the love to make sure I wasn't just catching the next generation people. So why should you care about this? Also wanted to pander to the Star Wars folks too. Why should you care about this stuff? There are kind of three major things that SDR brings to you, and they sound kind of abstract at first. One is the ability to do field programmable RF. You can, from a corporate perspective, you can actually ship a product that has an SDR built into it, and then you can just update how the radios work in firmware. That also helps us, as we'll see later, but that's one of the big kind of value propositions of SDR. The other thing is rapid prototyping. If you're an engineer building radios, you don't want to spend 2 weeks spinning a board, sending it out, getting it back. You can actually use an SDR, as we'll see later, to prototype a new radio design in minutes in some cases. And then the thing that we'll probably care most about with this audience is reverse engineering and the massive leap forward in capabilities we have to do reverse engineering with SDR. So, like I said, the field programmable RF, it's maybe sounds like more of a corporate thing or more of a product side thing, but being able to quickly build programmable scanners and tuners and demodulators and decoders, this is actually something that really benefits us when we're trying to see whether or not we have unexplained, suspicious, nefarious RF signals floating around an environment that maybe we don't want to know about, or that we want to know about because we don't want them doing whatever it is they're doing. Being able to set up that type of scanner in a very programmable way in minutes and configure it in seconds can be a real big advantage. Being able to sort of tune into stuff that is there that we maybe don't need to reverse engineer, but we just want to be able to tune in and analyze the signal, that can be also helpful. These are all things that SDRs enable. And then on the rapid prototyping side, that seems even more like an engineering function, but there is one aspect that is kind of interesting, and that is being able to build a customized transmitter and receiver. It's a great way to exfiltrate data from a site if that's what you're interested in doing. And just a simple Raspberry Pi connected with a very affordable and small form factor SDR with a little battery attached to it, and you've got yourself an interesting little exfiltration transmitter that you can transmit using all sorts of obscure digital modes that people are unlikely to think about. And yeah, so depending on what your particular InfoSec role is, there's a lot of interesting capabilities you can come up with. But the last class, somebody even mentioned, hey, I could actually build a kind of a two-stage exfiltration system where I'm flying a UAV over a potential target site and kind of uplinking to the UAV and then using the long-range transmitters on those things to blast it back. So I mean, there's a enormous space of opportunity here, I think. But reverse engineering is where most people land on the InfoSec side, and the thing that I can never impress enough upon folks is that the ability to capture raw RF signals, which is something SDRs allow you to do. They allow you to pull in signals from your computer, or signals from your environment rather, and stick it on a hard drive. And it's unbelievable how valuable that is when you're trying to reverse engineer something. And I think sometimes people hear that and they think, oh, you're capturing signals. And we sort of are, but we're not just capturing signals. We're actually when you set up an SDR to capture a chunk of the RF spectrum, you're actually capturing everything. That means if you had, to use like an FM radio example, you're not just kind of tuning into one station, you're tuning into all the stations on that band that you're capturing from. So you're getting 94.9, you're getting 97.1, you're getting all of them at once, and you're sticking them on a hard drive. And you're not just getting the signals, you're getting all the noise, you're getting all the other stuff that might be present at that point in time, which means you might find signals you didn't even know were there, but you captured them, so you have a chance to actually work with them. And so the big advantage of having the signal captured and on your hard drive is it lets you quickly experiment offline at your own leisure with all sorts of demodulation and decoding methods to kind of break down that signal. And kind of the way I like to talk about it, even though this key fob has absolutely nothing to do with that piece of ham radio gear, is that in the old days, if you were trying to reverse engineer a signal prior to having this capture ability, what you would end up with is somebody generating a signal. Let's say it's just a simple digital signal coming out of this key fob. And then you would have to basically set up all your equipment. You would have to guess, I think it's this type of protocol and this type of frequency and using this type of modulation, and you'd set up all your knobs, so to speak. And then if the transmission came in and you got a successful decode and demodulation, you're like, hey, cool. And if you didn't, well, you had to wait until the target pressed the button again. With the SDR approach and the signal capture or the RF capture capability, at this point, somebody presses their button, you're ready for it, you capture all the signals, all the noise in a big chunk of spectrum, and then you can just offline try all sorts of different ways to reverse engineer that to your heart's content. And you know, and there's processes that we'll explain in our next book that kind of let you sort of do a kind of a funneling in on the characteristics of based on the characteristics of the waveform to be able to kind of work your way down till you have the bits. Because ultimately you can do tons of stuff with SDR on the analog side, but most of the people I think tuning in here are not. I'm sure there's probably some hams on this, some ham radio folks on here, but primarily I'm guessing most people are interested in getting some bits and messing with those bits. So that's kind of the focus we're going to have here. So you have an idea of what it is. The next question might be, what do you do to get started? And it might seem daunting. And my hope is by the time we get through this podcast, or sorry, it's not a podcast, by the time we get through with this webcast, that it won't seem daunting. It'll actually seem super straightforward. What you see in that picture is really all you need. You've got a lot of the stuff already, and the key item is really a PC, preferably a PC that has a beefy CPU. This is one of those rare cases where the CPU matters dramatically. Like I don't know very many people that actually fully utilize the CPUs on their computers, but I think I'm actually one of those people. I've actually had my CPUs on its knees dozens of times trying to get stuff, crunched. Yes, it's you can see all the performance monitor cores are all spiking, and it's fans are all whirring up like crazy. So the more CPU, the better, but that shouldn't stop you if you don't necessarily have the new 8700K or better. You can still do a lot. Even with something like a Raspberry Pi, you can still do stuff. You just have to be more efficient and scale down your intentions. But with respect to the with respect to the PC, the CPU is important, and the actual storage can be important if you're going to do a lot of reverse engineering. The raw RF files that I've talked about that are so cool, they're also really big, and you can actually get multi-gigabyte files very quickly. So
Paul, Don has a question. When you say more CPUs, do you mean faster or more cores?
I mean, yes.
All the things.
The software that I focus mostly on, which is going to be gnuradio to give away something 20 slides from now, is actually built to be very competently multi-threaded and spread out its workload on multiple cores. So if you have one of those new 20-core Intel or AMD parts, you'll actually benefit from them in some certain circumstances if you actually have 20 parallel things going on. I actually ran into a situation on that UAV project I was mentioning, the drone project from a year ago, that I was able to demodulate and decode this incoming video stream. And then after a while, it would start to get flaky. And after debugging it, I realized what was going on is I was actually maxing out all 4 cores, all 8 threads, and then the laptop was starting to get too hot and the CPU was thermal throttling. So I actually had to go in and make a few efficiency enhancements because that's how hard I was abusing the system. So, but don't let that scare you off. Even if you've got, like, you can see a laptop back there. I think that's a 5-year-old Lenovo that I still use for stuff. So you get more capabilities. You can use the CPU, but there's usually ways around it if you don't have it. So cool. After you've got your PC, which hopefully, I mean, I'm assuming just about everybody on this podcast has at least one of those lying around. You're going to need some software, all of which is open source, fortunately. You're going to need some SDR hardware, and that SDR hardware is usually going to be a USB 2.0, some hopefully USB 3.0 in the better hardware, and then you've also got some Ethernet models and some PCIe stuff for some fancy folk. I'm not going to get into that level of stuff here. I'm probably not the place you want to start anyway. And then you really just need an antenna to screw into it. And a lot of the SDRs, they come with an antenna anyway. If you want to buy one, they're pretty cheap. So I want to start with how to choose the hardware. That's probably the thing that might be the murkiest at first. And the questions you want to ask is, how much can you spend? And I'm not selling them, so I'm only asking that for, you really do need to know that. There's a lot of variation. You can go from $20 up to $20,000 if you want to. What kind of performance or features do you need? And I'll kind of explain what features might even be possible in a slide or two. And then those are kind of the words you might see as you talk about that. And then how simple and stable do you expect the software to be? How easy do you expect the drivers to be? If you're the kind of person who's willing to hack at some stuff, a big kind of, Ubuntu jockey, then some of the less simple installation flows may be fine for you. If you really don't have a lot of time for that and you just want to get going today, then there's flows for that too, but it all just kind of factors into the choices you need to make here. So it's all about trade-offs. The way I look at it is you've got price, performance, and ease of use. And just like basically every engineering decision, you can have two, you can't have all three. So, and I really have no idea why the ancient alien guy is in this meme, but I felt like I needed to get him in here. So we can just check that off.
Because crazy.
I will not reference aliens any further in this podcast, which it's not. So here's kind of a description of the different kinds of things that are SDR specs, and a lot of them, they may have kind of funny sounding engineering words, but they're really pretty basic. You can see on whether something is full or half duplex, you might remember from maybe days of messing around with modems, but full just means you can transmit and receive at the same time. Half means you got to choose. And you're either transmitting or you need to flip to being a receiver, flip to being a transmitter. So some SDRs support half, some support full. Some even support multiple channels of full, so you can do all sorts of stuff. So that's one spec you might be interested in. The number of ADC and DAC bits is kind of in a more engineering way of saying how accurate are the measurements that the SDR is making of the real world signals. And what that manifests in is clearer signals when you're trying to work with them in the software later on. So preferably you want this number to be higher rather than lower. The Mac, excuse me, let me head off that. The maximum sample rate or the bandwidth, they're not exactly the same thing, but they tend to resolve into how many frequencies you can kind of look at the same time, whether or not, if we're to use the FM example, whether or not you can only look between channels 96 and 98, or maybe you can look from 94 all the way to 108. That's what the bandwidth or the maximum sample rate, they both feed into how wide a chunk of radio stuff you can look at. And then oscillator precision and frequency accuracy, that's not usually a big deal, but if you're, say, communicating from one SDR to another, then if there's some error between what the first SDR thinks of as 10 megahertz and what the other one thinks of as 10 megahertz, they're going to have trouble communicating, and you might have to kind of fine tune them. So the better SDRs, you don't really have to do that fine tuning stuff. It's got rock solid accuracy out of the box. Frequency ranges, not all SDRs can go, well, they can't, they have limits to how low or how high they can go in terms of their frequency operations. So you've got some ham radio people doing things at some very low frequencies. Most SDRs can't work in those. You've got some satellite microwave people doing stuff at crazy high frequencies, and most SDRs can't work with that out of the box. Now, if people have interest in that, I can talk about ways you can get around that, but frequency range is just something you want to think about if you're aware of a particular set of signals you want to mess with. And then FPGA gate count and transmit power, don't even worry about those. I can get into what that means, but that's going to be down the road for almost anyone working in SDR. So I'm going to kind of go through a little bit of a reverse triage, I guess, talking about what kind of SDR hardware I would recommend. If money's not really a big object and you're willing to blow $1,000 on an SDR or close to it, I would advise going straight to the Edis USRP devices. I'm not being paid by them, but I do use their products, and they are the easiest to get working. They have very good performance, multiple channels on some of them, full duplex on all of them, precise oscillators, so you don't have to worry about calibrating that stuff out. And they have a really great form factor too. This is the B200 Mini, really tiny. The antenna is actually probably more cumbersome than the actual SDR itself. So definitely a big fan of the Edis devices, but understand that if you're just starting out, maybe you don't want to blow $800 or more on a SDR. So there's also a great mid-range option. Michael Osman came out with the HackRF 1 a number of years back, and it's significantly more affordable at $300 or so, depending on where you get it and what kind of package you get with it. But you can do a lot, do a tremendous amount with the HackRF. It's not going to have, you'll notice it's got an 8-bit ADC instead of the 12-bit on the last one. So that means the signals aren't going to be as clear. They're not going to stick out from the noise quite as much. It's a half duplex device, meaning you can receive and you can transmit. You can't do them at the same time. The oscillator's not super precise, so if you were to set up a system where the HackRF 1 was talking to another HackRF 1, you'd definitely have to calibrate out the oscillator error in most cases. And it's pretty easy to install. I think almost as easy as the Edis devices. They basically one extra step, and you'll have your HackRF 1 working. So it's a great choice if the Edis parts are too rich for your blood. And if you really want to just start out with the basics.
Hey, Paul.
Yeah.
Back to that the HackRF
sure.
one. You said it's easy to install, but it requires an extra step. What's the extra step?
Oh, it's you just depending on your install flow, you just have to. I mean, I'll get into the specifics of the install flow later, but you just have to put the drivers and utilities. You have to get those via a different package than the gnuradio standard stuff. It's not a big deal though.
Okay.
Yeah. So if the $300 is too much and you just want to get started with the most simple, cheap way, not necessarily simple, but the cheapest way possible, then there's these interesting little gadgets out there called the RTL-SDR dongles. And they have kind of a fascinating history because they're not designed to be anything like what we're using them for. They are actually a digital television receiver that people were originally, they were sold to plug into people's computers, and then you can just watch digital television on your laptop. And it turns out that rather than build a product that does this with fixed function components, the engineers decided, well, it's easier to just use a low-cost SDR. And so we'll stick that in there. That way we can kind of tweak it with firmware updates based on stuff we learn about how the digital television standard changes, or supporting additional countries down the road, or whatever their rationale was. They had no interest in building these things to support the SDR hacker community. It just so turns out that people realized, hey, there's an SDR in these things. We can actually unlock that, put our own firmware on there, and create our own SDR. And since these things are only about $20 anyway, it's probably the cheapest way we can do that. And so sure enough, that's what we have here. And then companies like Noelec have actually kind of put their own cases, their own branding on the original hardware, which is kind of funny.
Nice.
No, it's a great it's a great story, because before this, people had actually found a way to use their sound cards in their computers to kind of hack them into being SDRs, which it's not the greatest, but it's free if you already got one. So that's it's really cool how people have made this. They really democratized this. They've made this accessible to just about anyone at this point. And so the downsides to using the RTL SDR is it's got an even lower resolution ADC. It's actually 8 bits, but you only really get 7 bits out of it effectively. And so you're basically you have half as much noise resistance as you did with the HackRF, which has an 8-bit A to D DAC system. And then you can't transmit with this. So the only thing you can do with this is look at signals, reverse engineer them. You can't actually create your own signals to do interesting things to the systems that you've reverse engineered. And then it doesn't actually, the frequencies range is much more compressed, and it varies a lot depending on which RTL SDR dongle you get. And so some of them you can't even go up to a gigahertz, others you can go a little over a gigahertz. It varies, but it's significantly less than like the HackRF, which will go up to I think 6 gigahertz, or the Edis devices, which are pretty similar.
We have a bunch of questions, so I'm not going to ask you all of them yet, but you mentioned like transmitting. So a couple people have asked, thank you, Martin and Samson, like what are the legal ramifications of transmitting?
Yes.
And can you tell us about that? Or I mean, if you get to that later, we can just hold off, but.
No, I can mention that now. Transmission is an interesting thing because the FCC retains authority over basically any kind of receiving and transmitting that gets done. And you can get licenses to do that. That's basically what the ham radio community are people who are licensed to build their own radios and utilize them. And the examination process for getting that ham license is basically, it's understanding technical stuff, but it's also understanding the rules under which you can transmit and what powers you can transmit at and what characteristics of the signals you transmit, what those are, and most importantly, what frequencies you're allowed to transmit on. And that's really the thing, is the FCC is kind of the traffic cop for radio stuff in general in this country. They've sort of, that's why when you are using your FM radio, all those FM stations are in the same range of frequencies. They're all between 88 and 108 megahertz. That's why your AM radios stations are all between, 600 and 1600 kilohertz. That's why your Wi-Fi routers are all using 2.4 and 5 gigahertz. They've basically defined who can transmit and where. One of the things that if you look at the rules and you follow them carefully, you actually don't need a license to transmit if you fall into a certain set of categories. One is if you're using the ISM bands, the industrial, scientific, and medical bands. There's some frequencies that are set aside for basically companies or individuals to prototype products and to even utilize products in these certain bands that have different licensing requirements. And as you're working on the prototypes, if you are, and this gets a little squishy, but if you're not transmitting constantly, but you have a low duty cycle is the technical term, you're only transmitting intermittently and relatively infrequently, and you're transmitting at sufficiently low powers, and you'd have to look up what those are, and you're transmitting in these bands, you can actually do stuff. If you want to run some kind of pirate radio station, that's a whole different thing. I think
because then you would always be transmitting stuff, right?
Well, you'd always be transmitting, but you're also likely transmitting at a higher power, otherwise nobody would be able to hear it. So you're transmitting at a higher power, and you also have the issues of one of the things that's required for, and the ham folks go through some training on this to get their certifications or to pass their tests. They need to know this, that there's you're supposed to identify who you are in some way, shape, or form. In most cases, if you're transmitting in a lot of different bands. And so if you're running a pirate radio station, I guess you could be identifying yourself, but it seems like it would defeat the purpose somewhat. So I think somebody asked prior to the show whether or not there's like squads of FCC, SWAT teams running around trying to find rogue transmitters and kick down doors. It is not the case, to my knowledge, that there are any of those that exist, but there is an interesting community of individuals that take it upon themselves to kind of find stuff that shouldn't be going on. And the ham community is a remarkably skilled group of people with respect to RF understanding. And they're not necessarily trained engineers in most cases, but they know an enormous amount. And there's a lot of free classes. If you want to get your ham license, you can go to these classes, and it is amazing how much these guys know about stuff. And they have this sort of like they have this sort of like community that really doesn't like people doing stuff they're not supposed to be doing, right? I mean, if you're transmitting in a way that is irresponsible in their mind, and oftentimes if you're transmitting in an illegal way, it is irresponsible. It's probably very, very similar. Then you are impacting the community of hams that are trying to do things right. And so they actually will take efforts to kind of find out when people are doing stuff they shouldn't be doing. And so, yes, the FCC doesn't have their hit squads, but
ham radio does.
There are a group of unhappy, and justly so, I think, unhappy hams that may report you to the FCC and may find out somewhat where you are. So
is this something that they would be upset with then, doing this stuff?
Well, no. This gets into using the SDRs responsibly. I mean, SDR is just another type of radio equipment at the end of the day. And if you are transmitting at very low power that doesn't even exit your office or your laboratory or whatever space you're working in, it's not going to be an issue. Now, I'm not saying legally that you're completely fine, because I'm not a lawyer. You should get a lawyer and talk to that lawyer. So feel free to put disclaimers below on the thing. But
you take no responsibility.
But keep in mind that every time you press a button on one of these things, you're generating a radio signal. If you use an SDR and you're playing around with your car trying to see how you get into it, and you generate a radio signal to get into your car that looks just like this thing, you're not really impacting the environment, the RF environment, that much. So the other thing to keep in mind, I said don't worry about transmit power on the slide before in terms of specs. One reason you don't have to worry about transmit power is none of these things are very powerful. When you're talking about just a mobile phone.
This is not what you would buy to start your pirate radio station.
No, you would need to get an external amplifier and a big antenna and all sorts of stuff that would then cause you to be on the FCC's and the other fellow hams radar. This is this is I think, what is it, 10 milliwatts or something output at, if you're in the right frequency band. If you're a little bit off to the side, it's less. I mean, 10 milliwatts is not a ton. And I mean, just to use RF power is kind of a squishy thing, and talking about how many watts will go how far is not really something you can do because there's so many factors and so many variables. But a fairly beefy drone control link was, I think, a 2 to 5 watt system, and that could go about 10 kilometers, maybe 20 on a clear day. So when you're talking about several orders of magnitude less than that, it's not going to go very far. Doesn't mean you should just leave your SDR transmitting on because you don't care. I mean, you know, be careful when you transmit, but and don't transmit on frequencies that, I mean, if you live right next to an airport, you should not be transmitting on frequencies that the airport is using. And you can look up what those are. It's not too hard. But yeah, in general, this isn't, I would say, a big issue.
Okay, cool. One other question, because we were talking, sorry, one other question from Samson.
Sure.
Do you recommend getting involved in ham radio before you move to SDR? Do you feel like there's value in understanding that?
There's definitely value in understanding that. There's a lot that you'll learn really quickly about practical radio technique and what I sometimes call RF hygiene. Just keeping things clean and keeping things well formed and well structured, but it's definitely not necessary. What I like to tell people is leap before you look with SDR. It's really easy to get going. It's really easy to get the software up and running. It's easy to mess with it. I would advise you maybe look before you transmit, but don't look before you just
don't overthink getting involved.
Absolutely not. Think twice before you transmit, maybe, but don't worry about it on the receive side. Just go ahead and jump in. It's fine.
Okay, cool.
The water's fine. So I want to give a mention to this fourth option, because I just mentioned 3 options: the expensive one, the mid-range, the cheap one, the affordable one. Sorry, but there's this really interesting thing emerging that it's not quite there yet in my view, but when it becomes there, I think it'll be huge. And that is a company out of the UK called Lime Microsystems produces something called a Lime SDR. They've got a small one, which I'm holding here, and they've got a larger one that has multiple channels to it. But this thing, on paper, has all the capabilities of the Edis product. So in theory, it should be just as good, only costs $140 instead of $800. Unfortunately, what we have is a situation where the drivers, the documentation, the installation flow, it's all still a little wonky. You can get it working, but it's not the easiest thing. So if you're the hacker type, or if you just want to kind of take a shot at something a little more exotic, I think it's a reasonable option. They're a crowd-funded thing, so it's not like there's some company that came out with a product and it wasn't ready. I mean, they said all along, this is crowd-funded, it's going to come out, we're going to have some glitches here and there, but we just want to get to the market as fast as possible. And so total respect for what they're doing, but just another option. It's a little early maybe, but something to consider. So I want to talk about software now, and specifically about the kinds of software that I believe is the best choice for SDR work. It's going to depend a lot on your operating system, and I very strongly believe Linux has the best stuff. You can get things working on Windows. Some of it's native built for Windows. Other stuff can be compiled for Windows. Other types of things can work. Sometimes it works better on Windows, sometimes it works better on Mac. Almost all of it is going to work more cleanly on a Linux box, and specifically Ubuntu 16.04. I've done some installations on 18.04, and it's unfortunately, there's still some weird stuff happening, so I can't really recommend 18.04 just yet. But if you have the ability to wipe off a partition, put a fresh 1604 on there, that's the easiest way to get going. But an existing 1604 partition should work fine too. Do not use a VM unless you want to give yourself a headache. It's anytime oftentimes at SDR classes, people used to bring their own computers to my SDR classes. Now I just supply all the SDR or all the SDR equipment and computers, just because it's so much simpler to have people sit down at a computer that's prepped, ready to go, has all the software, has all the files, boom. And so before that though, sometimes I would tell people, make sure you have this, and this software installed, come to class and we'll get started. There would always be some people that would come in with VMs, and it will sort of work, but as is always the case with VMs, the trickiest thing is to get the hardware driver interface working and working efficiently. And SDRs stream so much data over these USB ports that in almost every case I have seen problems. And when you start dropping data from that stream, your radio signal basically becomes garbage. So as tempting as it is, I would really recommend that you not use a VM. So in terms of the software, there's two basic types of software you might want to use. The first is these kind of GUIs that do simple scanning and demodulation. They're kind of one-stop shops. You click around in them and you see what's out there, you listen to things. That chunk of software is one basic type. The second basic type are software suites that you can use to actually program the SDR, or more accurately, it's actually not the best description there. It's not so much programming the SDR as much as it is programming the whole system. So basically things that allow you to build programmable radios, more like software development and coding essentially. All of these options are open source, which is nice. You shouldn't have to pay for any SDR software at this point in time anyway. So with respect to the scanning software, I'm not going to spend a ton of time on this, but they are kind of fun to play with when you first get started. Like I say, they're basically a graphical interface that will show you the radio information coming in at a certain segment of the RF spectrum, and you can kind of see these peaks indicate that there's some signals here, and then you can kind of click on those peaks, and then you can select the there's a lot of kind of things here you can select, but you can basically choose to interpret that signal that you've clicked on as being an AM radio signal or an FM radio signal or some ham radio mode, and then it will either play some audio if it gets some, or it'll give you static if you don't. And you can kind of tweak the knobs. These are really interesting and neat pieces of software. You can kind of hook them up to output some digital stuff if you go through some hoops, but it's not really my recommended usage of these things. This is more just an interesting kind of survey piece of software to see what's out there and play with your SDR. GQRX is the most commonly used and I think the most bulletproof choice for a Linux system, and works with just about every SDR under the sun. Has that cool FFT display, which stands for fast Fourier transform, but it's really just that picture of the frequencies, kind of where the frequencies on the x-axis like we just saw, and you see those peaks. That's really just what an FFT display looks like practically. And like I say, kind of point and click to demodulate your major audio modes. You've got AM, FM, narrowband FM, which is something used in some commercial applications, as well as some ham radio applications. Single sideband and continuous wave are ham radio modes that the software will work with, and it'll work with a few other things as well, but those are the major ones. I kind of view GQRX as being a little bit ham centric, but it's definitely, I think, a good starting point. It's easy to install and worth taking a look at.
Raphael had a question that kind of he asked a while ago, when you are looking at the RF signal, will the software determine the type of modulation to look at, which you just mentioned with that other one?
It will not. That's something you've got to figure out.
Okay.
Or
So it'll see all of it.
it'll see a peak, and then it'll see a peak maybe, and then the software, I don't use GQRX a whole lot. I don't believe it like automatically figures out the modulation. I think you would have to sort of click between the available ones just to see which one works.
Okay.
Yeah. So other options, there's an interesting package out there called SDR Angel that works a little bit like GQRX, but it also allows you to do some transmission, which is kind of cool. That one actually runs on Windows as well as Linux, and it kind of half runs on Mac. SDR Sharp is a big sort of Windows version of GQRX, for lack of a better description. That's actually, it's open sourced, I think, but it's run by a company now. The history of SDR Sharp is a little fuzzy, and I didn't use it a whole lot. HD-SDR is another option that's similar to that, but some of these are less likely to support your hardware than others, so you just want to take a look depending on what type of hardware you get. If you get one of the Edis boards or the HackRF boards, you should be fine though. So the other big group of software out there besides these kind of GQRX scanner type all-in-one bundles are programmable SDR software. That's the other kind of school of software out there. And you'll see what I put up here. I'm not going to go into all the pieces of this, but that's the kind of thing you're looking at with more of the programmable SDR software. You're basically either graphically in this case, or you actually can ignore the graphical stuff and just use Python or C code. That's what we're looking at this point. And the benefits to going this more programmable, deeper route is that you just have a lot more flexibility, a lot more powerful applications that you can make than with the simple scanning stuff like GQRX. You can build a lot more different types of radios. You can engage in reverse engineering that you really can't with GQRX. And the downside, of course, is there is a steeper learning curve, which I don't want to fib and tell you that there is no learning curve or that you'll figure it out in a day or 2 days. I will tell you though that the learning curve.
That's why they need to take your class at Black Hat.
Exactly. It's not don't be afraid. It's not as steep as it seems. You absolutely don't need to be an engineer. There's relatively little mathematics involved, and the stuff that there is very manageable. So yeah, just don't get scared. There's really only two major packages out there, gnuradio, and there's something out there, Pothos, which I haven't worked with as much, but I hear does some pretty fun things. I focus on gnuradio. It's a free open source platform, unbelievably feature rich. There are blocks that just handle dozens of RF modes out of the box, and you can add on software to do tons and tons more than that. It's a graphical input method like you saw on the slide before, but it also gives you APIs if you want to do C++ or Python coding, and it's a relatively straightforward thing to figure out how to do that. It can be installed on all the major OSs, but you're going to want to do it on Linux. I've gotten it working on Macs, I've gotten it working on PCs, and it's just not worth it. That's my view. So there are either in the box type of blocks that gnuradio has, or there's just a host of people that you can just go up in their GitHub and install their own blocks that you can easily plug in to gnuradio, or you have just complete applications that are built on the gnuradio APIs that do just about every wireless thing you can imagine. And as much as it may not be interesting to simply build an LTE base station or an LTE virtual handset, you might have some interest if you want to run an LTE network, but maybe at a different frequency, or maybe somebody else is doing that and you want to see why they are or what they're doing on those different frequencies. There's an incredible amount of programmability you get with SDR that allows you to work in these different technologies, but not necessarily color inside the lines, or detect other people who are not coloring inside the lines, so to speak. So yeah, kind of this last thing, there's a number of ways to get digital data out of gnuradio or out of a gnuradio based application so that you can shove it into Wireshark and do things that I think would be familiar to a lot of folks on this. I keep calling it a podcast in my head, but in this webcast.
It's
So,
all right. It's a cast. It's a cast of some
so
kind.
just quickly, how to install gnuradio. Easiest way, just use the package manager. It is going to give you basic functionality. You may have to install the drivers depending on which SDR you've got. Very quick and simple. You're done in 3 seconds, and you got something you can work with. You will get an older version of gnuradio if you do this, 3.7.10. Doesn't sound like that's so much different than 3.7.12, the latest, but they have added a ton of stuff recently, so that is a downside. The other option you can do is you can go through something called PyBombs, which is basically a utility that builds gnuradio from source and builds a lot of drivers and other things as well. It probably takes over an hour on most systems. It's not a quick process. You have to go through a bunch of different commands and Ubuntu incantations to get it working. Oh, I got the pros and cons swapped. So it is not a con that you get newer software, and it's not a pro that it takes that long. But sorry, I'll fix this before we post this. The thing is, though, you don't have to do this alone. I've got PyBombs walkthrough for Ubuntu 16.04. You can download basically chapter 2 from our books, which is always here's how you install the software. And so it'll walk you through every step of that. You can just go ahead and download the PDF from our website. And if you want to go the package manager based route that also installs a bunch of drivers for all sorts of different things, I've put up a script on GitHub, and this actually contains the install script. There's a bunch of gnuradio flow graphs or programs, so to speak, that you can also use to kind of test out your setup, which can be kind of useful. Some kind of digital radios. If you've got 2 SDRs especially, it's kind of cool to be able to just set up a receiver and a transmitter and have stuff work, give you a sanity check. So in the few minutes left here, I want to go through a very, very high level walkthrough of what working in gnuradio looks like. I'm not going to dig into it. I'm not going to drop blocks on in a demo form. I'm just going to kind of give you, well, I have no idea why this Austrian guy is jumping out of this plane, but I think that dog's got the coolest job ever. That's the height we're talking about here. So basically, I'm going to give you 2 minutes at most of how a radio is put together, maybe 1 minute on how gnuradio works at the highest possible level, and then I'll show you 2 flow graphs or programs so you can see what that is. So on the receive side, basically every radio on Earth, and if you take the way SDR out of here, this works for fixed function radios too, is you've got the let's focus on the SDR side though, just to simplify it. You've got the SDR producing data that's coming through that USB port in most cases, coming into your computer. You do some kind of tuning, meaning you're focusing on one signal and then ignoring all the others, getting rid of all the others. And then you're taking that good signal that you've kind of tuned to and you're demodulating it. You're taking all those kind of analog radio squiggles and you're turning it into something else. And then you've got, at the end of that process, what we'll call your baseband, which has a slightly different definition in radio world than it does in some other telecom contexts. But what it means is basically the signal that you're trying to get. That means digital bits, or it means analog stuff like voice. That's what every radio receiver looks like. On the SDR side, we just have to build those different pieces. And so gnuradio is a software package. You can think of it as 3 elements. You got sources that allow data to come in to your program or your flow graph. You've got blocks that mess with that data. And then you've got syncs where the data goes out and does something. And so I've got here an FM receiver. This flow graph is all you need to do to use an SDR to get FM broadcast signals and listen to them. Up at the top, I've got a bunch of variables just like you'd have in any program. And then here in the rest of the flow graph, I've got a little block that connects to the SDR and brings data from the SDR into the flow graph. I've got this block which does all the tuning, kind of figures out what signal you want and filters out everything else and gets rid of all the stuff you don't care about. It's got a demodulator that turns that good chunk of signal into your baseband signal, which is in this case voice. And then it's got these 3 blocks that all they do is they kind of tweak that baseband signal to kind of clean it up and make sure it works with the source, or the sync, sorry, the baseband output, which is just the sound card on your computer. This may not be that interesting to somebody wanting to get into some deep InfoSec bit wrangling, but it's the same format as if you were to work with a digital radio. The same basic blocks are there. You just use slightly different techniques. So when you run this flow graph here, you're going to get the frequency display here, or the FFT display. All these little peaks are FM radio signals. You can kind of tune it, set the volume. This is what the FM radio flow graph is going to do. If I show you the digital side, you got a lot of similar blocks. You got the SDR block, it goes into a tuner. It's actually the same tuner block. We got a few extra things. We got a squelch block. We got a demodulator block, which is the same thing as we had in the previous. And we got a few more of these things before you send it out to a sync where you can actually look at the results. But ultimately, if I run this digital flow graph, I'll get bits here that come out. Now you can actually see the bits or the digital data printed out there. So the quick summary here, use Ubuntu 16.04 for now. My recommendation is just go ahead and grab my GitHub install script and use that, and you can get that at the link there. Go ahead and play with the Git bundle flow graphs. They're different flow graphs for each of the major. Well, each of the Lime, Edis, and HackRF, they all have some flow graphs that you can just use out of the box there. And then this little Python script will tell you which SDR you should buy. Basically, if you can afford the Edis, get that. If you can't, but you can afford the HackRF, get that. Otherwise, buy the RTL-SDR. And then that's pretty much it. Just questions. If you have a question next week or 2 months from now, you can go ahead and there's contact info on the Factoria Labs website. You can send an email to Paul at Factoria Labs if you want to. I've got a Twitter feed. Upcoming trainings, like I mentioned, DC area in June, Black Hat Vegas. And if you want to just get links to all of that stuff, you can just go to my website under training and you'll be able to do that. So cool. Boom, I actually finished a minute late.
Well, it was because you would have finished, okay. Except for I interrupted you with a minute of shirt pandering.
No, that's important stuff.
Okay, so we do have a question, another question from Samson, who has had so many good questions. So yeah. Thanks for being on, Samson.
Sure.
So do you have antenna recommendations?
So yeah, I do. One thing that is really neat is I think everyone should have this guy here, some kind of telescoping antenna. That this actually comes free with the HackRF. And the one thing, and book 2 of our series goes through this, there's only about 3 pages of stuff you need to know, and you can easily figure it out online. But there's something called an SMA connector, which almost all of the SDRs you're going to use have this SMA connector here. And so That's the only thing you want to make sure is you get the right one, and don't get RP SMA. That's this weird thing the FCC made the Wi-Fi people do so that you couldn't swap out antennas easily. So avoid RP SMA unless you have an adapter of some sort, which you probably don't. So this is what I would start with, because the way our RF works with respect to receiving it with antennas is that the length of the antenna is going to influence what frequencies it's good at picking up. And so if you're trying to pick up a lower frequency, you'll actually extend it, and a higher frequency, you'll retract it. The other thing you can do, though, because they are remarkably affordable, you can see this little guy here, which I've got this kind of cheap label maker label on. This is a 433 megahertz antenna, and it's nice sometimes when you know you're working with a specific band of frequencies, not to have to worry about the retraction and the extension, but rather just to get something that is always optimized for the frequency in question. So 433, there's a lot of stuff that operates at 433. 315, which is where a lot of the car key fobs in the United States are located. If you know you're going to play around with car key fobs and spend some time hacking them, then go to Amazon and spend $8 on a 315 megahertz antenna, and it's just a lot simpler and cleaner. Now, the number and types of antennas out there is essentially infinite. You can get something like this that is an LTE antenna that actually has multiple elements in here so that it can receive and transmit at the kind of the lower 700 to 900 band, as well as the higher multi-gigahertz band. So, and these aren't that much either. I think this was $10. So it's not a bad idea to just build, if you're going to work in this area, to just build a little kit with 5 or 10 antennas in it. And they don't cost that much.
Cool. Okay, so his second question is, are you able to jam signals using SDR?
You definitely can. The transmit power thing that I talked about earlier, it gets into that, because you can jam any signal if you're close enough and you have enough power, or some trade-off of the two. I don't know if you remember this is the most physics I'm going to get into, but if you remember the inverse square law, that just means that the signal, if a signal is emanating in all directions, you start to lose power, not linearly as you go further away, but much faster than that. And so that means it's much easier for me to jam something 1 meter away than 10 meters away. Vastly easier. So you can use the HackRF without any external amplifiers to jam things like the car key fob thing is kind of a nice starter project for a lot of folks. And one of the things that you can do is you can actually jam the 315 megahertz band where they're trying to operate on, such that they can't get into their car. Now, there are reasons why you want to do that, and some man-in-the-middle stuff that makes that useful. But you do that basically just by transmitting a simple tone that doesn't really do anything. It just a basic signal with no data or anything in it at right about 315 megahertz, and the key fob won't work. So just as a sort of a practical, I don't know, rule of thumb, if you're working with the HackRF, you can jam, and you're working at max power, you can jam somebody trying to get into their car from maybe 20 feet away. And that's, that's going to vary based on the conditions, but that's the kind of rule of thumb. You're not going to jam somebody across a football field with something like this. For that, you're going to need a directional antenna and or a power amplifier.
No, but these are good ways to annoy your neighbors, and by good I mean terrible ways.
So yeah, or yeah, if they've got like an RF remote, like on their TiVo or something like that, yes, you can do that. If you wanted to be a terrible citizen, yes.
Okay, there's another question, and this is kind of a more practical question. I have a lake house in the middle of nowhere, and I wanted to make a cell phone signal repeater. Using the Blade RF40, could I achieve this without breaking laws? I realize it would be transmitting constantly, but it would basically just be repeating the signal that's already there, right? What else would I need if I wanted LTE?
So there's an open LTE package out there that can allow you to transform a computer plus SDR into a base station essentially. And if you're operating that, so let me just say it's probably illegal.
But I'm not a lawyer.
If you were to operate that in the middle of nowhere, whether or not anyone would know or do anything about that is another question, but I'm pretty sure that you're not supposed to be doing that. They do actually sell repeaters for exactly that purpose, but I know that costs a few $100. I've been told though, and this may not be the cool SDR route that I should be evangelizing, but I've been told that if you walk into your cell phone provider and you complain about cell phone coverage, that sometimes they'll give you a discount on those things and you can get them for like $100. So yeah.
Good.
I think it is possible. I mean, I know it's possible,
but maybe not advisable.
The problem is, though, here's the thing. The problem is, and let me think about this a little more. You probably are not going to be able to integrate into the network is the problem. So building the extender, I think that's going to be the issue. Is you can't necessarily integrate into the network. You're going to be able to build your own base station, but it's basically going to operate. It's basically going to be like operating your own cell phone network. So let me retract what I said a little bit. Is you can probably operate your own cell network with that Blade RF. Well, I know you can. We've done that, but legally. But you won't. You can't just splice into whatever it is T-Mobile, Verizon, or Sprint is doing.
So you wouldn't be able to like use
and pass
your
calls
cell phone.
like that. Yeah, in terms of the boosting thing, I mean, I think if what the caller is asking about, like I'm on a radio show, if what you're asking about is can you simply use it like a forwarding thing, like a signal's coming in, I'm going to forward that, and then I'm going to use the other channel to, or the full duplex mode to basically, yeah, I mean, I'm thinking about this through this on the fly. I think if you wanted to do that, you'd probably need a 2-channel SDR where you're actually, and then you run into problem. Yeah, I think, I don't know if you've ever played around with Wi-Fi repeaters, but those things can sometimes get sketchy because you've got sometimes interference between the original device transmitting and you've got the repeater, the extender, and I would probably not go down that route if I were you.
So the long answer was
sorry for the long-winded answer.
Don't do it.
It was a little bit more of a thought experiment that I thought had a more obvious answer at first, and then maybe not so much.
Okay, another question from Daniel is encryption a problem or is everything sent as plain text? And a couple people have asked this in some form of or else. Another.
Encryption is definitely a problem for Bluetooth, Wi-Fi. Lots of times, I know there's been cases where protocols like Z-Wave will support encryption, but that doesn't necessarily mean that it's being used by the manufacturer of the IoT device that you might be trying to mess with. So encryption is definitely something that you need to be aware of, but it's not always there. And other times you got things that are like encryption, like rolling codes on the car key fobs, which is, it's not exactly encryption, but it's kind of similar to it, where you can sometimes do something about that, but not always.
Okay. And then one more, or two more actually. Marcin asked a while ago, so we're just getting back to it. How fast can you exfil data with SDR?
Oh, pretty fast if you want to. So to get a little bit more into RF engineering, just as a general rule of thumb, the speed at which you can transmit data is going to be proportional to the bandwidth that you're consuming. And so even something as affordable as the HackRF is going to support 20 megahertz bandwidth. So you can actually shove data out of this thing pretty quickly if you want to. Now, it's not exactly 20 megahertz that you're outputting. It's going to depend on the mode you use and a bunch of different things. And Professor Shannon has some things to say about that. But ultimately, it's roughly proportional. So you can transmit megabits worth of data out of this thing if you wanted to. take some power, and it'd be probably not the best way. Also, if you're exfilling data, you probably want to be a little bit more surreptitious, and using a big chunk of 20 megahertz makes you stand out a little bit more. But if you needed to, yeah, you could dump data out pretty quickly.
Okay, David Fletcher asked, have you used Red Hawk? Is it as powerful as GRC?
I have not. I have seen I've seen it. I think I've got so invested in the not the GRC for the training, and then I've sort of built a lot of sort of code that calls gnuradio APIs, and so I've kind of invested myself a little bit in that ecosystem, and so I really haven't looked outside as much as perhaps I could have.
Cool.
You're always finding yourself kind of grabbing utilities that you've used in the past, and I got a few things on GitHub that may or may not be useful to people, but
okay, cool. All right, well, that is it for questions. So there's still like a lot of you on, if you want to go ahead, Paul, and explain these blocks to us.
Yeah, and again, this is still going to be maybe a 5,000-foot view, not so much the deep dive, but just so you can kind of get an idea of, I mean, what I want you to get from this flow graph is that this stuff is a little tricky, but it's not super tricky. This is stuff that if you learn 6 or 7 things, this will make sense. And so I'll kind of show at the high level what those 6 or 7 things would be. I mean, you've got the SDR that is set up to bring data into the flow graph. We talked about that in the other FM flow graph as well. We've got this filter, which if we look at this, the filter, it's called a FIR translating filter, but ultimately all that block does is it sort of tunes, or it centers in on, let's say, for example, this peak. If we type in the right number, it'll go to this peak right here, and then it'll use a filter to basically sort of keep all the stuff close to that peak, and then it'll just get rid of everything on either side. And my books are books that get a lot into filters and how they work, and you actually probably know a lot more about filtering than you think you do out there, because maybe you've messed with your car stereo, or if you've done some stuff that if you just connect the dots, it'll be usually a light bulb going off in people's heads, like, oh, I guess I do know about filtering and frequencies. I just didn't think about it that much. So that's all this block does, though, is it just isolates the signal you want and gets rid of the stuff you don't want. There's this block called a power squelch. All that does is say, you know, lots of times there's noise. I don't want to listen to noise. I don't want to try to figure out what digital bits are in noise, because there's nothing in noise. It's random junk. But when the signal gets up above a certain point, then I want to start trying to turn it into bits. That's all the squelch block does. And it has a little level that you set between this is signal and this is noise and garbage. Next, we've got a GFSK block, which that's called Gaussian frequency shift keying, which is, this block does an amazing amount of stuff. And you don't need to know a ton to use it. Yet it helps to understand what frequency shift keying is, but all that really means is that a transmitter is sending out 2 frequencies. When it wants to send out a 0, it'll send out the first frequency. And then when it wants to send you a 1, it'll change to a different frequency. That's all that is. The other thing that this block does is it handles the timing. It actually determines, hey, 10 milliseconds went by, for example. That's 1 bit. So I'm going to output a 0 or a 1. And then I'm going to wait 10 milliseconds. I'm going to do the other. That's the kind of the timing aspect of this. Because this whole flow graph is operating at 2 megahertz. And so that means that there's 2 million pieces of radio data going through this every second. You don't have, in this case, 2 million bits per second. You don't have a 2 megabit per second digital link here. And so this block also, besides converting the radio into digital, it also kind of converts this big super high frequency stream of digital into the lower frequency bits. And that may not be entirely obvious, but it's actually one of the harder things about receiving digital streams, is figuring out, hey, what's a bit? Do I have a 0 here, or do I have 2 zeros in a row, or do I have 3 zeros in a row? That's something that takes some thought. This correlate access code tag stream is a horribly named block. And if you've worked with Ethernet stuff, you might have come across the concept of a preamble, but all that means is a certain binary pattern denotes, hey, I'm starting a new packet, or I'm starting a new transmission. And so the access code is just 0101. It's basically 5555 and in hex. And anytime it sees that exact pattern, the correlate access code is going to tag the bit stream and say, hey, a new packet's starting, or a new transmission is starting. And then repacking the bits just means it's going to take individual ones and zeros and pack them into bytes. And then this tagged stream to PDU, PDU is called as a protocol data unit. And this is a cool thing that gnuradio lets you do, where instead of just working in bits and radio samples, it allows you to kind of transform into this new boundary where you're now using a higher level concept called messaging, or PDUs, which are kind of the format that you can store a message in. I'm hand waving a little bit there, but you can see actually how that happens, because you get this kind of transformation from this kind of purple input to this gray output. That just means a different kind of data is being handled in the flow graph. Like here it's blue in the very beginning because that's kind of radio data coming in. And then after the demodulation, we don't have radio data anymore, we got digital data. And then we go through here and now we've got message data. And we go to a message debug sync, which if you look at the output here, that's what's printing out in the console window, is this, hey, I've got a message debug and I found a PDU that's 13 bytes long and here's the contents of it. Now this is kind of a debug thing. You could do something a lot more interesting with this if you wrote a Python script that wrapped around it and then took the data and dumped it to a file, or put it to a display, or made it control some other thing. I mean, all that's possible.
Nice.
Yeah, and then you can see here, this is the actual digital data that's being displayed, where each little dot is one bit, and you can see the beginning, it's got these up downs. That's the 5555 of the preamble. But yeah, and it just repeats over and over again. So, and this was actually taken with this screenshot was taken from operation of the flow graphs that I included in that GitHub project I pointed you guys to. So you can, if you have two different SDRs, you can actually run this, and yeah, in that GitHub bundle there.
Nice. Cool. Well, thanks for explaining all that.
Sure.
We had a bunch of people that already left, but they wanted to thank you for an awesome webcast, and we really appreciate you being on. This is super interesting. If you guys are wanting to dive deeper into this, Paul is teaching a class on SDR at Black Hat. So, and you can email him at paul@factorialabs.com.
That's right.
Cool.
Yeah, well, thank you very much. I appreciate the opportunity to be here, Sierra and John and all at Black Hat, or at Black Hills.
Too much black.
Yeah, and yeah, thanks everyone for signing on and listening.
Mike says, great podcast.
Yes.
Or radio show, or whatever this is. Callers, we appreciate you being on, and we will catch you later. Thank you. Bye-bye.
Bye all.